Hello and welcome to this lesson video where we will learn about the identification of work scopes of the concrete structures and the calculation of the material and work quantities. The lesson learning objectives are as shown. Concrete is one of the very fundamental building materials, and it is made using four ingredients: Portland cement, water, aggregate, and additives. The proportions of these ingredients are determined through its mix design that considers three main objectives. The concrete mix is designed to achieve a strength capacity within a specific time period, in addition to other life cycle performance goals like permeability and resistance to specific chemicals. Also, the concrete should be designed to be easily mixed to provide acceptable workability levels to end up with a quality structure with a homogeneous material. These design criteria are validated using different tests like the cube sample, compressive testing to confirm the strength capacity of the mix. Workability is assessed using the slump test. The more the slump, the more the workability. We can see that more workability is needed for concrete elements with heavy steel reinforcements like walls, columns, and beams. The least workability is needed in mass concrete, like concrete dams. The Portland cement is the most known ingredient of the concrete mix. It's produced in large cement production plants and mostly delivered in package bags of around 94 pounds each. Cement can be delivered in loose quantities for large production settings like concrete batch plants or large construction projects. There are 5 standard cement types for different purposes as shown. The water is the second ingredient as it causes the hydration chemical transformation of the cement. This is why water needs to be clean from foreign materials like organic material, acids, salts, to avoid side reactions from occurring, which may weaken the concrete or interfere with the hydration process. Aggregates include gravel and sand, and they contribute to the strength of the concrete. The bonding between the aggregate and cement binder is important, and this is why aggregates need to be clean and should not absorb a lot of water that's necessary for the cement hydration. Finally, additives and admixtures are included in the concrete mix design to control or improve specific performance aspects of the concrete like strength, workability, durability, and constructability. Fly ashes are finely divided residue resulting from the combustion of ground or powered coal. In addition to its economic and ecological benefits, the use of fly ash in concrete improves its workability, reduces segregation, bleeding, heat evolution, and permeability. Inhibits also alkali aggregate reaction and enhances sulfate resistance. On the other hand, air entrainment is the process whereby many small air bubbles are incorporated into the concrete and become part of the matrix that binds the aggregate together in the hardened concrete. Air entrainment additives and their created air bubbles increase the freeze-thaw durability of concrete. Water-reducing admixtures are groups of products that are added to concrete to achieve certain workability and slump value at lower water to cement ratios. Additive retarders to the concrete mix delays the hydration of cement without affecting the long-term mechanical properties that improve the concrete constructability in situations where mixing and placing occurs at distant times, like in long distance hauling between the batch plants and the site. Accelerating admixtures are added to the concrete either to increase the rate of early strength development or shorten the time of setting, or both. Chemical compositions of accelerators include soluble chlorides, carbonites, and silica. Superplasticizers are water-reducing additives that are added to the mix to produce flowing concrete with very high slump in the range of 7 to 9 inches, which is useful in heavily reinforced structures with no adequate access for consolidation vibration. Superplasticizers can help to produce high-strength concrete. In some cases, we'll need to calculate the quantities of the concrete ingredients. This is the case for the concrete batch plant or the contractor of a large project where the concrete is mixed and produced on site. There are 4 specification parameters to look for to calculate the material quantities as shown here. Also, the estimate calculation requires knowing basic properties and unit transformation values, like the cement specific gravity and the cubic feet to gallon transformation. Most of the calculation depends on using the shown formula to calculate the volume of an ingredient based on its weight, specific gravity, and the water density of 62.4 pounds per cubic feet. The quantity calculations include the shown 6 steps. The goal is to find the weight of the 3 main ingredients, cement, gravel, and sand. This is done by first finding the volume amount of the different ingredients and then using the weight formula from the previous slide. Please look for the exercise video to see an example of these calculations. In bidding concrete work, contractors need to identify the different work packages and extract their quantities from the project drawings. The shown list is not an exhaustive list, but it provides the most common work items in constructing a concrete structure. Let's check each one of them. Calculating the volumes of concrete depends on visualizing the structure and dealing with its geometry. It's great that most concrete structures are geometry friendly and are composed of simply 3D geometry shapes like cubes and cylinders. The shown cross-section is for a concrete drainage channel. To find the concrete volume, we will need to find from other drawing sheets the third dimension or the length of the length of the channel to calculate the volume as the cross-sectional area times the length. The challenge is to calculate these values following the work sequence of constructing the structure. For the drainage channel structure, we should not calculate the total concrete volume. We need to break it down to 2 volumes, the footing and the walls, because they are constructed separately. It's good practice to detail your estimate quantities for one work item, as these values can be recycled for other work items. Concrete formwork is a sophisticated sector of the construction industry that needs a whole course to learn its systems, design, and methods. We will try to cover the basic knowledge here of the different systems and the estimate of their rough high-level quantities. A typical formwork can be simplified by saying it's composed of a sheathing that forms the face of the concrete structure and a temporary structure that holds the sheathing in place and resist the concrete weight until the structure is self-sufficient. For slab wood formwork, we can see that sheathing is supported by an array of joists and stringers that are supported on shores and bracings. Recently, modular formwork is becoming very popular uh, uh, due to its easy installation. This photo shows a column formwork that's laterally supported by diagonal struts. Wall formwork has a similar anatomy to column formwork. In large structures, the formwork panels are held laterally by using cross ties that are embedded into the formwork and removed later with the form, leaving behind the tube holes that need to be filled, as we'll cover in dry finish treatment work. Similar to the concrete volume, formwork quantities are organized following their structural elements like beams, columns, and walls. A formwork quantity that's usually forgotten is the bulkhead, which is located at the edge of wall and slab segments that are in the middle of a longitudinal structure. We will need here to differentiate between two quantities related to each formwork item, its installation and fabrication. Formwork installation is quantified initially using its contact surface area or square foot contact area, SFCA, as commonly used in the US. As part of the bid cost and contractor the bid cost, the contractor needs to account for the cost of fabricating the formwork elements and panels. But formwork is typically recycled within the same project and between projects. For a specific job, a fraction of the formwork fabrication is considered with each installation. This means that the formwork fabrication quantity assigned to a job is the same as its installation quantity, but divided by the number of times this formwork will be used. This table shows some use values for example formwork elements. For example, the slab formwork is expected to be used 10 times before it is salvaged. We are used more wall or formwork is used more times as they have more uniform surface. Bulkhead forms are used the least, as they are customized for every edge to pass through the reinforcement and other accessories between the wall or slab segments. Going back to the channel example, the wall formwork on both sides can be calculated as the length of the wall times the length of the wall segment. Remember, we need to form only the concrete vertical faces and bottom faces that need to be formed. The bottom of the slab is already formed by the natural ground, and the bottom of the wall is already formed by the top of the slab that's poured before the wall. The top of the wall does not need structurally need formwork, and it is finished by the placement crew. The bulkhead formwork for the walls and slabs is quantified using the shown area, which is done at each edge joint between the channel segments. Although it's not part of the concrete structure, the soil under the foundation needs to be fine graded and compacted to provide a clean surface for the concrete, rebar, and formwork crews. The civil contractor who excavated the soil is typically required to finish the soil to the required foundation elevation with a rough tolerance that's not sufficient to create quality bottom surface of the foundation. Also, finishing the soil before placing the concrete is helpful to avoid settlements at some spots below the concrete structure, especially when dealing with high traffic sidewalks. For the drainage channel, the soil contact area is the width of the slab times the length of the channel. The construction joints, especially the horizontal ones between the different concrete structure segments, need to be cleaned before the next concrete placement. This is done by pressure washing or sand blasting. For example, the joint between the walls and slab on the channel need to be sand blasted before placing the concrete or the wall, or the concrete of the walls. The top horizontal face of the concrete does not need to be formed, but it needs to be finished, especially if it will be visible with architectural value. Concrete finish entails screeding, floating, and troweling. Screeding is the same of striking off the excess concrete to the desired surface level. Floating removes the irregularities on the surface of the concrete which are left after screeding. Troweling is the last step to have smooth, hard, and abrasion resistant surface. It can be done with a simple hand or bar trowels or powered trowels that you can even sit and ride them. So cool. Any concrete surface is in direct contact with the air may require special treatment to keep it moist or prevent the concrete inside moisture from evaporating. This can be done by periodically soaking or spraying the concrete with water. Also, protective barriers can be applied on the surface, like polyethylene sheets or curing compound spray. We see here that all surfaces that are considered for the concrete channel except for the bottom surface of the slab, as it is not in direct contact with the air, and of course because it's not accessible after pouring. We use the term dry finish to refer to any concrete surface covered by a formwork, and it's covered by a formwork and is first seen after removing the form and excuse me, and it is almost dry. Concrete dry surfaces are subject to all kinds of defects that can come from poor concrete consolidation, like honeycombs, poor formwork alignment, like the joint offsets or fins, or intentional holes from formwork ties. The treatment of these defects depend on if the surface is exposed or not and visible to the eye after the structure is completed. They are treated by grinding the fence or grouting the holes and voids. For the example structure, the outside dry faces after removing the formwork require non-exposed treatment, as they will be covered after the soil with the soil around the structure is backfilled. The inside faces of the walls will require a higher level of treatment, as it is considered an exposed dry surface. Steel reinforcement can be estimated in rough or detailed quantities. This table shows very rough rebar quantity estimates for different structural concrete elements. Rebar detailed quantities for different bar sizes and shapes can be estimated, but they are beyond the scope of this course. Finally, contractors need to pay attention to any miscellaneous items embedded in the concrete structure, like embedded steel plates, anchors, or water spouts. For the example structure, water stops are inserted in the bulkheads of the walls and slabs between the successive segments of the structure. They are measured in linear distance. Wow, that's quite a list of quantities here. This type of detailed quantity takeoff is expected to be done by specialty contractors like concrete contractors. Look for the exercise videos for examples on concrete ingredient and work quantities. Thanks for watching and hope you enjoyed the lesson.